are considered together because they are sister tests. That is to say, in most of the time, they give the same result. But there are some differences which we will not be concerned with at this point. Okay, the tests in the form we will consider them is the following. Okay. Let AN be positive ultimately. This is necessary for a ratio test. And, okay, AN is greater than or equal to 0 ultimately for root test. Okay. Then, one, if limit of the ratio is L, and it is strictly less than 1, then the series converges. Now, in the root case, you look at the limit of the nth root is L less than. Conclusion is the same. Okay. 2, if limit is bigger than 1, or L is infinity, okay, then the series diverges. Okay. Again, this is the ratio test case. For the other one, you look at the limit AN to the power 1 over n is L bigger than 1, or L is infinity, then this diverges. This is the root test case. Now, these two are the basic conclusions. But of course, there's a possibility that L is 1. Firstly, because ultimately AN is positive, these limits cannot have a negative value. But they can be 0, okay, which is included in this case. Okay. Or they can be infinity, which is included in this case. Or the limits may not exist at all. That, of course, makes the use of this test impossible. But it can be 1. Or limit AN to the 1 over n is 1. Then test fails. Now, test fails means that it doesn't say anything. So then, okay. Now these are very practical tests, but their use, okay, should be carried out with care. Let us see why these are comparison tests again. Let us prove the first one. Okay. So suppose limit of the ratio is L and it is strictly less than 1. Okay. Then take any R between 1 and L. Okay. Then, with epsilon, okay, R minus L, sorry, there exists an N0 such that an plus 1 over n over an minus L is less than epsilon, which is R minus L. Okay. In particular, okay, well, at this point, let me say that because ANs are ultimately positive, I can choose the values N0 a little bit larger so that this is true and AN is positive. Actually, strictly positive. Okay. So I have two conditions to be true. That is, by choosing n a little bit larger, and this will hold for all n greater than n0. Well, then, we get the following. An plus 1 over an would be smaller than, okay, R. Because this is an plus 1 minus an minus L is smaller than the right side in absolute value. Without absolute value, it's still small. So we get this. When for all n after n0. Okay. Thus, okay, if I look at an0, or just an, I can write it in the following form. Okay. You can see that if you carry the cancellations out, we did actually nothing. Because ANs are strictly positive after N0, we can do these things. Now, each of the ratios is smaller than R. And this is true, okay? Well, how many R's we have, of course, is exactly, okay, n minus N0. Let me check if I'm correct. You have this minus, that's right. So you have this, and an0. In other words, an is less than, okay, an0 divided by r to the n0 times r to the n. And it's true, ultimately. Now, because ANs are positive at the same time, okay, by comparison theorem, because the bigger one is convergent, so the series of AN is also. Well, it follows that the series starting with 1 is convergent. note that in the proof, we see that whatever technicalities we have in the proof, there is a comparison with a geometric series. So this is indeed a comparison with some geometric series. But it's done implicitly. Okay. Let me try to give a hint on the proof of 2. Okay. Now here we have limit of the ratio L, and it's bigger than. So, okay, take some R between 1 and L. Then with epsilon L minus R, it's a positive number, okay, there exists an N0 such that for all N after that, we have this ratio minus L less than, okay, epsilon, that is L minus L. Okay. Now, as in the previous case, okay, we can choose N0 so large that this is true and AN is positive. Because ultimately AN was positive. But then, okay, if we look at, okay, this inequality, we see that L minus AN plus 1 divided by AN is less than the absolute value, and it is less than L minus L. Now this says that, of course, it's true after N0. So R is smaller than this ratio. As in the previous case. Okay. We have a multiple of R, okay, smaller than AN, but we have here, okay, a constant. Let me not worry about that. For some constant C and greater than N. Okay. Now R is greater than 1, so the series by comparison the series has the series starting with 1 is also divergent. Okay. So in both cases, we compare the given series with the geometric series. Let me shortly comment on the remaining cases very shortly. Okay. Now, if limit of the nth root is L, okay, then, okay, then if L is less than 1, and this is true, okay, as in the previous case, we get this term less than r. Okay, for all n after sum n is 0. Well, now it's easier to continue. So an is less than r to the n is greater than n0. Use comparison theorem, etc. Okay. Finally, for part 3, that is as a proof of the third case, that is limit an plus 1 over an is 1, okay, then no conclusion. Okay. Just consider 1 over n and 1 over n squared. In both cases, limit of the ratio or limit of the nth root is 1, but okay, the first one is divergent. Okay, is divergent. And the second one is convergent. So you cannot say definitely that you always have convergence or that you always have divergence. Okay. Now, let us consider some examples. P any real number. Okay. Whatever P is, positive or negative, okay, or 0, we see that an is positive for every. So we have no positivity question here. Well, then we look at the ratio. So we are using the ratio test. That would say you have n plus 1 to the p divided by 2 to the n plus 1, that is an plus 1, divided by n to the p over 2 to the n, which happens to be n plus 1 over n to the power p multiplied by 1/2. Now, whatever p is, the limit when n goes to infinity would be 1 times 1/2. It's less than 1, so series converges by ratio test. Or consider an to the power 1 over. Okay. Because we have positive terms, this is possible. It is n to the 1 over n to the power p divided by, okay, just 2. Now, limit n to the 1 over n is 1, since limit x going to infinity, x to the 1 over x is 1. Okay, you can check this. So this goes to 1/2 less than 1. So series converge by root test. So this example vaguely shows that the root and ratio tests more or less give the same result. Okay. Actually, except for a few peculiar examples, they always give the same result. Okay. Let us consider a second example. See here. Now, except for 1, n equal to 1, all the terms are strictly positive. Okay. So an logarithm n to the power 2n divided by 2n to the n is always non-negative in the first place. Now, note that unlike the previous example, where we could use both root or ratio tests directly, okay, it is not always the same with the same easiness depending on the terms in the general term an. For example, note that we have the nth powers in both cases, and the root test takes the nth root. So it would be very simple here. Okay? And therefore, okay, since we have nth powers, okay, ratio test seems easy. So we apply it. The nth root, okay, would be logarithm n squared divided by 2n. Now, this limit obviously is 0. The reason is limit x going to infinity, logarithm x squared over 2x is 0 using L'Hopital's rule. But then 0 is less than 1. So the series is converged by root test. So, because we take the nth root in the root test, okay, if we have a lot of nth powers in the terms, okay, of the expression for an, root test seems to be easier. But on the other hand, a very particular case happens if we have factorials dancing around. Namely, okay, then in the next example, right, we have 2n factorial, 2 to the n to the 2n. Let me check. Right. Okay. Well, now since the nth root of a factorial is problematic, that is, okay, we do not know what this is. Because in the factorial, you have a product, and if you have the nth root, you don't have a nice closed form, no simplifications. Because this is problematic, with factorials, appearing, we do not want to use ratio test, root test. Okay. But with factorials, if you use the ratio test, that is putting n plus 1 instead of n, okay, still gives you a factorial, and you have cancellations. So ratio test should be preferred. Okay. Firstly, okay, an 2n factorial 2 to the n divided by n to the 2n is positive for all n. So then, we look at an plus 1 divided by a. Now, an plus 1 says that you replace n with n plus 1 wherever you see it. This is an plus 1. Now, an was 2n factorial, 2 to the n over n to the 2n. Now, the idea here is to simplify things as much as possible. Well, this, of course, is quite direct. Note that here we have 2n plus 2 factorial, 2 to the n, times 2, divided by n plus 1 to the power 2n, and then n plus 1 squared divided by 2n factorial, 2 to the n, divided by n to the 2n. Now, we see directly that these cancel out. And we observe that this term is 2n factorial times 2n plus 1 times 2n plus 2. So they also cancel out. In other words, we have here 2n plus 1 times 2n plus 2 times 2, okay, divided by, here we have n plus 1 to the power 2n times n plus 1 squared, and 2n factorial was cancelled out, okay, but we still have this term, n to the 2n. Over here. Wait a minute. Something is wrong. So it is up here. Okay. Now, when we look at these terms, we can still put them into a nicer form. Okay. Let me rewrite it in that form. This is 2n plus 1, 2n plus 2 times 2, okay, divided by n plus 1 squared times, I will put this term below the first one, 1 over n plus 1 over n to the power 2n. Now, I do this to put it into a more understandable form. This is, of course, 1 plus 1 over n to the power n squared. And clearly, the limit here, okay, when n goes to infinity, because n squared cancels with the n squared at the top, you end up with 8. This, of course, goes to e squared. So the whole thing goes to 8 over e squared. Now, this term, one can easily calculate that, would be greater than 1. So series diverge by ratio test. Okay. Well, I will have one more example on these root ratio tests. Let me set that up. Okay, here the general term an is given by a product in both numerator and the denominator. So it is 1, 3, 5, up to 2n minus 1. And at the bottom, it is up to 2n plus 1, 3n plus 1. So for the first term, when n is 1, you end up with 4. For the second one, you have 7. And for 3, you have 10, and so on. Okay. Complicated, it may seem. Okay. We have some observations in the first place. An is the product so it is positive all the time. But before I proceed, let us see what we will understand from this. This means the following. For example, A1 means that you put n equal to 1. If you put n equal to 1, you multiply all odd numbers, starting with 1, up to 1. But there is only one of them. So this is 1 at the top. At the bottom, you multiply all these numbers up to 4. But you only have 4 here. So the first one is 1 over 4. For the second one, now, when you put n equal to 2, it says you multiply all odd integers up to 3, starting with 1. So it is 1, 3. Similarly, at the bottom, 4, 7. A3 would be 1, 3, 5, divided by 4, 7, 10, and so on. So the meaning of such a product form means exactly this, and it tells you where to stop. So n tells you where to stop. Now, because of this, okay, a n plus 1 would be, you put n plus 1 instead of n. But it's a product. So before the term here that you multiply with n plus 1, you have the term with n. So this would be all products up to 2n minus 1, but you have an extra term where you have this. Okay. Similarly at the bottom, you start with 4, 7, 10. You have 3n plus 1, but you have the last term where n is replaced with n plus 1. Okay. Now, you don't have to calculate all of those, of course. It's enough to look at what an was. It was 135 up to 2n minus 1, because you stop at the nth term, and you have at the bottom 3n plus 1. So the ratio is very simple to calculate. You have the same part here and here. So the ratio is just 2n plus 1 divided by 3n plus 4. Okay. Now, because the general term is given in product form, now product form looks like factorial, of course. You can express both of them in terms of factorials, by the way. So we preferred to use the ratio test instead of the root test. It would be a mess here to use the root test. You could not go anywhere with that. It would not be practical. Okay. Theoretically, it would be the same. But here, of course, the limit when n goes to infinity is nice enough, less than 1. So series converge. Okay. By ratio test. Okay. Right, finally, I want to have a comment about these 3 tests that we considered. Okay. Let me use this board. Okay. All of the 3 tests, namely the integral test, okay, comparison test, as well as limit comparison test, okay, and finally root ratio tests, okay, are comparison tests. Namely, okay, the integral test compares a given series with an improper integral. Comparison or limit comparison test compares a given series with another series. Finally, the root and ratio tests compares a given series with a geometric series. Okay. As such, okay, we have to be careful about the usage of these tests. In particular, if AN does not have fast increasing terms like exponentials, factorials, n to the n, and so on. Okay. Even if it's positive, and you can apply the ratio root tests, okay, the ratio root tests give L equal to 1. So, are inapplicable. Okay. So the conclusion, do not lose time to apply them. Okay, again, if you don't have such fast increasing terms in AN, the root ratio tests are not useful. They would give L equal to 1 because they compare it with a geometric series. Okay. Let me give you a particular example which will explain this view. For example, okay, one cannot show convergence divergence of, say, 1 over n squared, okay, which we know from elsewhere, okay, by comparing it with a geometric series. Okay, let us see how such a comparison could be made. It says that this is a positive series, yes. You compare it to show convergence with some r to the n, okay, where r is less than 1. Then you can say the series here is convergent, the geometric series, so the smaller one is also convergent. But this never happens. This inequality is always wrong. Okay, because r is less than 1. Or, to show divergence, assuming we don't know the result, okay, you need to show the following. A geometric series is less than 1 over n squared, and r is greater than 1, so that this is divergent. And this will be divergent as well. Okay. This is, let me add, this is to show, okay, sum 1 over n squared is convergent by comparison with a geometric series. And this is to show this series is divergent, again, by comparison with a geometric series. Okay. To show, in comparing with a geometric series, that this one is divergent, it is not, but suppose we don't know it, you have to show such an inequality where r is greater than 1. Of course, this is nonsense. This is out of the question. Okay, this is always wrong. So you cannot compare with a geometric series at all, for convergence or for divergence. So you have to be careful about the terms you have in your general term an.